Hi, my name is Carmen Al Masri. I'm an intern at Harmonic Discovery, and I've been working with the Harmonic team on modeling kinases in the active state using ColabFold with a custom MSA approach. To give a quick background, kinases are proteins that are essential for cellular regulation, and their dysregulation is associated with multiple types of cancers and autoimmune diseases. This makes kinases prime targets for drug discovery. Kinases are dynamic proteins, and their catalytic domain can switch between multiple conformational states. The kinases exist in an equilibrium of active and inactive states. We define the active state as the conformation where the conserved alpha C helix and the aspartate of the TFG motif are both oriented towards the active site. When they're oriented away from it, then the kinase is inactive. Each of those four conformational states determine both the structure and the pharmacokinetic properties of the molecules that can bind to the active site of the kinase. From a structure-based drug design point of view, we would ideally want a given kinase to be available in a desired conformational state, but in the PDB, the structures are mostly in the active or CIDI conformation, the rest are inactive, and most kinases are not represented by multiple conformations in the PDB. One workaround is the computational modeling of the kinases in the desired conformation. We were particularly interested in seeing if AlphaFold can be used for those purposes. We want AlphaFold to be able to generate a kinase in a certain conformation, and there are three main parameters that we can modify, three main parameters or inputs that we can modify. First, there's the multiple sequence alignment input, or the MSA, the PDB or template input, and the number of recycling steps to refine the prediction. We first wanted to see if AlphaFold can capture at all the conformational diversity of the kinases. And we saw that not only it can predict models in all conformations, but that the conformations very closely mimicked what is available in the PDB. Next, we wanted to see if we can use those models for drug discovery. We did that by comparing the docking enrichment of the AlphaFold modeled kinases to both apo and holo structures in the PDB. We found that for the active models, or the CIDI states, the model enriched better than the apo structures in the PDB and just as well as the holo structures. Oh, sorry. Sorry. Is this good? Okay. For the inactive conformations, the performance wasn't as good, and the holo structures enriched better than the AlphaFold models. So we wanted to mainly predict kinases in the active conformation, given the good potential that they showed. So the next step was to see if we can use the AlphaFold to generate kinases across the kinome in the active conformation, and whether we can use those models in structure-based drug discovery. We mainly focused on modifying the multiple sequence alignment input. We did that by using, instead of the default ColabFold MSA, the Modi-Dumbrak kinase alignment. This is a structurally validated alignment of all 500 human kinases, and it's estimated to be about 97% accurate and aims to have the minimum number of gaps in the alignment. We used the Modi-Dumbrak alignment and only kept kinases that have a certain number of active structures in the PDB and that have a sequence similarity within a certain threshold to the query sequence. So each of the kinases we're querying had its own custom MSA. We were also interested in seeing whether increasing the number of recycles would improve the accuracy of the prediction or increase the chances of getting an active structure. We found that the custom MSA did significantly increase the chances at getting an active structure, but only within a certain range of the MSA depth. When the MSA depth is too low, we're increasing our chances actually at getting an inactive structure. And when the MSA depth is too high, then we're significantly decreasing the chance of getting an active structure. So we found the ideal set of parameters for us to stay in this MSA depth range here between 20 and 50 is to use this setup here, which is to keep kinases with at least one active conformation in the PDB, to keep kinases that have a sequence similarity beyond the 0th quantile to the query sequence, and keep kinases with the percent of CIDI also beyond the 0th quantile. We also saw that increasing the number of recycles had absolutely no effect on either the quality of the structure or the probability of getting an active structure, so we just kept it at 3 recycles. We tested those parameters on a benchmark data set. At first, we tested the predictions on the default ColabFold MSA, and only about 50% of the structures were predicted as active, and multiple kinases did not have any active models predicted. Using the Modi-Dumbrach alignment with all 500 kinases, the percent increased significantly. It became 80% of the kinases, but we still had a few kinases that had no active conformation predicted. Using our custom MSA, we obtained 90% of the structures to be active, and all of the kinases in the benchmark data set had at least one active conformation. Now, this benchmark data set was chosen because it consisted of kinases that had at least one active conformation in the PDB, but that was not predicted by AlphaFold to be active. After obtaining the active structure, we proceeded to compare the RMSD of those models to the structures in the PDB. And we found that using all 3 alignments, the RMSDs were exceptionally low, which indicates that AlphaFold models the structures with high quality. We did notice that, in general, a higher MSA depth would be associated with a more accurate structure, but usually the model minimum performed at least as well as the default ColabFold MSA that had the longest MSA depth. After using our parameter set, we proceeded to generate kinase models across the entire kinome. And we again got 90% of the structures to be active, and all of the RMSDs were very low. The next step was to see if we could use those models in structure-based drug discovery. We particularly focused on the FLT3 kinase throughout the workflow because it had no active structures in the PDB, and previously obtained structures were through homology modeling, but the most similar kinase to FLT3 was CSF1R, which is only about 60% similar. This is the general drug discovery workflow. I'll go through it very briefly. We first want to identify a list of compounds that are most likely to be type 1 inhibitor. We then want to dock those molecules into the AlphaFold modeled kinase. The kinome binding predictor is a machine learning model that can predict whether the compound is active or not on the kinase. And then we purchase and test whatever compounds was filtered. So this is the first step here, which is to identify compounds that are first kinase inhibitors. We define the kinase inhibitor as a molecule that can bind to at least one kinase within 100 nanomolars. We also made sure that none of those molecules are known FLT3 binders. We were left with about 120,000 compounds. We then only kept compounds that are most likely to be type 1 inhibitors. Type 1 meaning they target the kinase in the active conformation. We ran a similarity search between our compounds and all the compounds in the PDB that are bound to a kinase in the active state, and we were left with about 1,500 molecules. We then proceeded to dock those molecules on the AlphaFold modeled FLT3. So if the molecule is actually a type 1 binder, it should be able to fit in the binding pocket of FLT3 decently well. We only kept compounds that had an RMSD lower than 3 angstroms to the reference in the PDB. After that step, only about 200 compounds were retained. Finally, we used the kinome binding predictor, which is a custom graph-based deep learning model that outperforms all established models for predicting kinome binding profiles. And the kinome binding predictor predicted that out of those 200 compounds, 45 are active against FLT3. We also ran an analog search and found 5 additional compounds that are potential FLT3 inhibitors. And out of all those compounds, only 8 were found to be purchasable. We then proceeded to experimentally test those compounds on 2 different assays. The FLT3 inhibition assay here is the assay that binds the FLT3 in the DFG-in conformation, so that would make it a type 1 inhibitor. And the auto-inhibition assay binds the kinase in the DFG-out conformation. So if the model is valid, we want the drugs to bind in the DFG-in conformation, but not DFG-out. These are the results that we got. They're actually very, very nice results. Out of all of those 8 compounds, 7 were found to have a strong bind affinity to FLT3. And out of those 8 compounds, 4 actually were preferentially bound to the FLT3 in the DFG-in conformation. So we believe that the AlphaFold model that we have for FLT3 has been validated. So we showed that AlphaFold can produce structures in high quality that can be leveraged for kinase drug discovery. We experimentally validated the FLT3 active model with DFG-in ligands, and we're currently working on making a library of AlphaFold models accessible to the public. I would like to thank the Harmonic team for all the help and support. It's been amazing to work with them. If you're attending at the ACS meeting, I highly recommend you attending the Francesco and Ryan's talks. Annalise also presented yesterday. I also highly encourage you to watch her talk. And thank you all for being here.
Thank you very much for the next part. Let's have the questions.
Oh, go back.
Very nice talk here. So my question is, I want to make sure I understand you correctly. You define the active conformation. So is that referred to ATP binding conformation or constitutes intrinsic active conformation due to the mutation? So when you build your model, have you kind of select those conformation when you're building your machine learning model? Yeah.
Yes. So the active conformation here is defined as the conformation that allows for the ATP to bind in the binding pocket, in the active site. And there are very specific criteria for that, including the orientation of the aspartate and the phenylalanine in the DFG motif, and also the positioning and orientation of the alpha C helix. So these are very distinct criteria that have been established.